All right, so we're looking here at linear and angular velocity, and we're extending this from what we did earlier in the chapter. So we reviewed these formulas, angular and linear velocity. We now have omega to represent angular velocity. So make sure that you do make note of this notation here, that this is omega for angular velocity. For linear velocity, we just have v. So we're going to use that v for our linear velocity. All right. The other thing that we looked at today is we looked at when will the linear velocities and angular velocities be the same. So we found out that linear velocity here will be the same when we have gears that are working together. So here we have this blue gear and then we have the pink gear. Because their teeth meet and work together there, they're going to have the same linear velocities. Also in a pulley system, this belt that goes around these pulleys has to have the same linear velocity at all points. So no matter whether it's the point that you're following, if you're following a point here, whether you're following this point and that point is moving around the large circle or the small circle, it has to be moving at the same speed the entire time. So those will have the same linear velocities as well. Now for angular velocities, we can see that our angular velocity is going to be the same when we have items that are on the same axle or the same center. So here we have this green gear and then the pink gear that are on the same center. So those two there are going to have the same angular velocity. All right, let's take a look at some examples. Number one, ship's propeller. It says the propellers on an average freighter have a radius of 4 feet. Okay, at full speed ahead, let me go ahead and label that. At full speed ahead, the propeller turns at 150 RPM. So this is 4 feet, and we know that this is 150 RPM. Remembering that RPM is rotations per minute. The first thing that it's asking me to do is it's asking me to find the angular velocity in radian per minute at the tip of the blade. So we're going to imagine a point that's going to be right here on the tip of the blade. So right here at the end. So it's 4 feet from the center. Okay, so for part A then, we're looking for angular velocity. So I'm going to call it omega. I'm going to say omega for the tip as well. So omega is going to be, well, we know it's 150 revolutions per minute. So we're just going to convert that into radian. So 1 revolution is 2 pi radian. So then we can go ahead and we can cancel out our revolutions, and we end up with 300 pi radian per minute. And that's the angular velocity at the tip. All right, well then it's asking us to find the angular velocity at the center of the propeller. Well, angular velocity is angular displacement over time. So if you have a point that's here at the center, it has no angular displacement. It's going to be 0. So that means that the angular velocity at the center is simply going to be 0 radian per minute, because that angle is not actually moving because your point is exactly at the center. All right, looking at part B. Part B asks us, what is the linear velocity in feet per minute at the tip of the blade? Okay, so now here we're looking for linear velocity. All right, so part B, linear velocity at the tip. Well, we know the relationship between angular and linear, so it's just going to be the radius at the tip times the angular velocity at the tip. So my radius at the tip is 4 feet times my angular velocity, I already know, is 300 pi radian per minute. So I can calculate that and I get 1,200 feet per minute. And that is my linear velocity at the tip. All right. The second part of this says, well, what about at the center of the propeller? Well, again, since 1, the radius is 0, then it's going to be the radius at the center times the angular velocity at the center. Well, both of those are 0, so it's simply going to be 0 feet per minute. All right, there's example number 1. Okay, let's take a look at number 2. So here we have a pulley problem. So go ahead and read this question. A large pulley, 20 centimeters in diameter. So I'm going to label it on my diagram though in radius. So 10 centimeters as a radius. Drives a small pulley, 6 centimeters in diameter. So I'm going to label that as 3 centimeters. And we have a pulley belt that goes over the rim of each. The large pulley has an angular velocity of 150 radian per minute. So the angular velocity is 150 radian per minute. All right. So part A, what is the linear velocity of the large pulley's rim? Okay, so let's go ahead and find that. The linear velocity of the large pulley, so I'm going to call it linear velocity of L for large. And it's the rim, so it's talking about like a point that's going to be on that belt that goes around. So here I know that that's going to be the angular velocity times the radius. So it's the angular velocity of the large one times the radius of the large. So I can plug that in, so that's 150 radian per minute times my radius, which is 10 centimeters. And so now I simply go ahead and I am going to calculate that. And so then I get my answer here of 1,500 centimeters per minute. And that's the linear velocity of the large one. I'm just going to go ahead and put that on my diagram. So V of the large is 1,500 centimeters per minute. I like to label those so that if I need to use them later, I know exactly where to find them, and it's really easy to find them. Okay, part B. What is the linear velocity of the small pulley's rim? So I want the linear velocity of the small pulley's rim. So if I'm thinking about that same formula, it's the angular velocity of the small times the radius of the small. Well, I know my radius is 3, but I don't know the angular velocity of the small pulley's rim. The angular velocities of the two are not the same, but I do know that the linear velocities are the same. So rather than using this formula here, I know that the linear velocity of the small is equal to the linear velocity of the large. And I just found that in part A, so that's going to be equal to 1,500 centimeters per minute as well. And I'm going to go ahead and just label that here. Linear velocity is equal to 1,500 centimeters per minute. Awesome. All right, continuing on with part C. What is the angular velocity of the small pulley? All right, well, I know the linear velocity of the small pulley, and I know the relationship between linear and angular. So the linear velocity of the small is equal to the radius of the small times the angular of the small. So my linear velocity is 1,500 centimeters per minute, and you always want to make sure that your units match. I have 3 centimeters times the angular velocity of the small. So my units match, my centimeters will cancel, and then I'll just be left with radian per minute. So that means that my angular velocity of the small, I'm going to divide by 3 on both sides, gives me 500 radian per minute. All right. And it makes sense if you just compare that my angular velocity of the small is 500 here. The angular velocity of the large was 150 radian per minute. So it makes sense that the small one is greater because it has to rotate many more times to keep up with the linear speed of the large gear or of the large pulley. Okay, let's look at another example. Here we have gears. So a large gear of diameter 30 centimeters. Again, I'm going to label that as a radius so I don't accidentally plug in a diameter instead of a radius, 15 centimeters there, is revolving at 45 RPM. So that's not angular velocity, it's just RPM. And then my small gear has a diameter of 8, so a radius of 4 centimeters. Okay, and they're connected in this way. So let's start with part A. Part A, how many radian per minute is the large gear turning? So radian per minute here is angular velocity. So I want the angular velocity of the large. So I take my 45 revolutions per minute and I multiply it by 2 pi radian per 1 revolution to get my answer of the angular velocity of the large pulley is simply going to be 90 pi radian per minute. Perfect. And I'm going to go ahead and just put that on here. angular velocity is 90 pi. And my units. Okay, then I'm going to continue on with part B. Well, what is the linear velocity of the teeth on the large gear? Okay, so we're still working on the large gear. So I want the linear velocity. Well, I know my radius and I know my angular, so I want the radius. Oops, that should be an L, not a V. Radius of the large times the angular of the large. And it's good to use these subscripts because these subscripts are going to kind of help keep everything organized. It's organized for you, and then it's also organized for me. Okay, so when I'm reading your work, I can easily figure out what you're describing. So the linear velocity of the large, then I just multiply those two together and I get 1,350 pi centimeters per minute. All right, so I'm going to throw that on here as well. So linear velocity is 1,350 pi centimeters per minute. All right, part C. How many radian per minute? Oops, that's D. Part C, what is the linear velocity of the teeth on the small gear? So I want the linear velocity of the small. Well, I just found the linear velocity of the large and I see that they're connected, right? So that's going to equal the linear velocity of the large. So that's also 1,350 pi centimeters per minute. All right, now we're ready for part D. Part D, how many radian per minute? So radian per minute is going to be angular velocity. Is the small gear turning? All right, well, I know the radius and I know the linear velocity. So I know that linear velocity of the small is the radius times its angular velocity. So my linear velocity is 1350 pi centimeters per minute. My radius is 4 centimeters, and then times its angular velocity. So I just calculate that and make sure my units match up so I can cancel my centimeters. And I divide and I get that my angular velocity is 337.5 pi radian per minute, which is 675 over 2. So 675 pi over 2 radian per minute. All right. And then last part D. So one more part here, part D. How many revolutions per minute is the small gear turning? Okay, so this isn't any angular or linear, we just want RPM now. Well, I know the angular velocity. The angular velocity of 677 pi over 2, and this is radian per minute. So a radian per 2 minutes. I'm just going to multiply that by 2 pi radian per 1 revolution. So now I can cancel out radians and I'm left with revolutions per minute, and that's exactly what I want. And so I just calculate that. I can also cancel my pi's. Pi cancels in the numerator and denominator. And I end up with that's equal to 675 over 4 revolutions per minute. All right, and so that concludes the extension of angular and linear velocities.